We, the team at trinamiX, would like to introduce a novel method to measure distances. We call it Focus-Induced Photoresponse, or just FIP. Here is a simple setup for measuring distances with a modulated LED light source, a camera lens, the FIP photodetector, and a lock-in amplifier to read out the signal of the photodetector.
The FIP effect for measuring distances relies on very particular properties of the photodetectors. In this experiment, we're using so-called solid-state, dye-sensitized solar cells. This type of photovoltaic device features a thin dye layer to absorb the light. Photo-generated holes are then extracted through an organic, solid hole transporting layer, whereas the electrons have to diffuse through a mesoporous titanium film. And this transport is very, very slow. Mesoporous titania is full of traps that hamper the movement of the charge carriers. However, these traps can be filled up with an increasing concentration of photo-generated electrons. In other words, the more focused and concentrated the light, the faster the generated charge carriers.
The effect can be seen here. As we focus the exact same amount of light in a smaller area, the photocurrent increases. The charges move faster. The highest photocurrent can be measured when the light is perfectly focused. The current decreases symmetrically as the light spot widens again. Therefore, we call the effect Focus-Induced Photoresponse, FIP. We now continue to focus the light by moving the sensor behind the lens and measuring the photocurrent. We repeat this for various distances between the LED and the camera lens. Each of the photocurrent curves corresponds to one LED distance. The maximum is located where the light is in focus. The peaks move closer to the focal plane as the LED's distance increases. They converge towards the focal length of the lens.
So how can we use the FIP effect to actually measure distances? One challenge to overcome is that the FIP effect is not the only contribution to the photocurrent. In fact, we find that in the dye-sensitized solar cells we're using in this experiment, the photocurrent is dominated by the amount of light that is collected through the camera lens. And this decreases roughly with the square of the distance between the light source and the camera lens. This means that if you wanted to extract distance information using a single photodetector, you would have to know exactly what the intensity of your light source is.
We solve this problem by using a stack of two identical sensors. The detectors are semi-transparent. Hence, light that is not absorbed by the front cell reaches the rear one. We divide the photocurrent of both sensors. The quotient value is steadily increasing with the LED distance. Thus, there is a unique quotient value for every LED distance. Without the FIP effect, the quotient for all distances would be constant. The LED can be moved around freely. We measure the photoresponse of each sensor and divide one by the other. The actual distance is then directly read from the quotient curve. No additional computation is needed. FIP can also work with multiple light sources. In this example, we have one fixed and one movable light source. Two light spots can be seen on the detector stack. The LEDs are modulated with different frequencies, and the sensor signal at each frequency is read out separately. Both sensors can be moved at the same time, and their distances can be measured independently. FIP is very versatile. Not only actively emitting light sources can be tracked, but also reflected light spots. The origin of the light has no impact, a real advantage over systems based on triangulation or LiDAR.
FIP is by no means limited to dye-sensitized solar cells. We've observed the FIP effect in various solar cell and photodetector technologies, thin-film devices based on materials such as amorphous silicon, cadmium telluride, CCTS, or organic bulk heterojunctions all show the FIP effect. Organic PV is particularly attractive as these devices can be made semi-transparent easily. Even infrared photodetectors based on lead sulfide photoconductors show a FIP effect. This means that we can use light from the UV all the way to the infrared range for our FIP technique. We believe that smart engineering of photodetectors can optimize the FIP effect. This will make FIP even more versatile and pave the way to sensing applications that have never been possible before.
Experience adaptive 3D sensing by trinamiX.